All right. Good morning. I'm humbled to speak here. It's a really great pleasure to see all the old friends and meet new ones. Thank you, Isam, for the invitation. Bob and I actually know each other through a mutual friend, Sandy Napel. I think probably Sandy is a mutual friend with many of you guys. So we actually, had many interactions over the years. Bob came to Stanford a few times, gave us seminars. I remember the last time he came to Stanford, I feel that he is so well respected and can give a lot of advice to our junior faculty. So I actually when I meet with him, I brought my junior faculty together with me and say, hey, this is the guy you must meet and to get some advice for the rest of your career. I'm talking about imaging, radiomics, and AI. I mean, really, I feel that these three topics are interacting. It's hard to say that AI is changing the imaging and the radiomics. I feel that, oftentimes I feel that imaging and the radiomics is changing the AI because, just a second. Physics, let's start from physics. I'm a medical physicist. So I don't think, many of you see this quote, and physics really changed the world, laid the foundation for the modern science. And I think you also agree. I mean, today, when we talk about data, when we talk about imaging, really, the data and the data science is changing our decision-making process, okay? And it's not an easy task, really. By now, when we talk about data science, I mean, we know that we still have a long way to go. There's a lot of challenge, really, for AI or radiomics or imaging really changed medicine. So there are a lot of challenge. The first challenge is really, the number of diseases is huge, right? There are about 20,000-30,000 diseases, and that actually doesn't count on subtype and then staging of different type of diseases, etc. And a lot of computer model. How are you going to really utilize this different type of model to model so many diseases? And also the data. We have so many different type of data, and they EHR and radiomics, imaging, different type of imaging, right? So I feel that the radiomics is really bridging the gap between different type of data, especially the tabular high dimensional data and the imaging. So now when you talk about AI, talk about the data, really, I think you only have one type of data, which is high dimensional data. And imaging, that's the famous paper by Bob. The imaging is data, and actually, data is also imaging. So I think the radiomics really bridging the gap between all different type of data, right? So, I think another challenge that the modern AI is facing is really the noisy data and sample, right? The data sample is small, and also a lot of time you have a missing data. So, and nowadays we have a lot of machine data too. So that actually we do a lot of modeling on the machine performance, etc. That actually also very interesting that the AI is changing that field. quickly. So talk about imaging. The complexity comes from multimodality and also the CT/MR, PET, and also planar image, etc. So how really you're going to come up with a model that can model so many imaging modalities and come up with an inference. So let's just begin with really just some basic. I feel that deep learning is really just a mapping, right, from X to Y, and depends on X and Y. You can divide them into 3 different type of applications. And the first type of application is input output are the same data domain. What do I mean here? If you input let's say a fuzzy image and you try to get a high resolution image, that belong to this category. So we did a lot of those calculation, along the same line. You can actually, mapping using deep learning to map from let's say low resolution dose calculation to a high resolution, right? And that save you time. Or you can even use a low cost computer algorithm, like a AAA to a Monte Carlo dose distribution. So that actually gone to next level. And even further, you can actually go from retracing and then go to high resolution, high quality image, a dose. So that is really just a dose calculation, right? So, with the state-of-art transformer neural network, we are talking about the sub-second dose calculation. I mean, this is really something that we had never imagined, like 5-10 years ago, we can do a Monte Carlo quality dose calculation within sub-second, okay? And, with deep learning, that has become a reality. And, the same principle actually applies to many, many other data, like a genomics data. You have a lot of missing, noisy data, and you need to do a gene, like an imputation. So with deep learning, you can do it so much better than the conventional interpolation type approach. So the second type of application, input and output, basically are different representation of the same subject. So what do I mean here? Like image reconstruction, right? You have a raw data, CT projection or MR case-based data. You want to convert that into a image. That's just a different representation. So let's just go to there. Conventional way, it's you use analytical or iterative model to convert the raw data or the one presentation to the other. So with deep learning, you can actually bypass that process. You can take a lot of prior knowledge and then do your image reconstruction, so-called data-driven image reconstruction. So this is the traditional way you do a CT imaging. And you need a lot of projection, typically 800 to 1,000 projection, and then you do an analytical reconstruction. So now with data-driven, you can go extremely sparse image reconstruction. So how sparse we can go, and so this is the process. If you plot, imagine you have a plot, number projection, and on the vertical axis, that's your level of prior knowledge. If you don't have any prior knowledge, and this is where we are today in the commercial product, right? Every patient is a new patient. You take a 1,000 projection, you reconstruct. And about 10 years ago, a lot of people work on compressed sensing. So where you actually introduce some image domain prior knowledge, and then you can reduce the number projection. So with the deep learning, you can really push that to the limit. So for this, in the case of CT, we are seeing that we can get one very high quality image with a single projection and plus prior knowledge, of course. And the same thing actually applies to MRI. So this is what's the original network. We actually have a new generation network that includes some imaging geometry. By doing that, you inform the deep learning model. So the deep learning model doesn't have to learn the geometry, right? So that gave you a lot of improvement in image quality or in the robustness. Okay, so what you're seeing here is a fluoroscopic projection image, and then you can actually use that to reconstruct a 4D CT image. Okay, and the same thing applies to MRI. You can use one projection equivalent case-based data, and then to get a MRI image. So that actually applies to Cartesian sampling, or it also applies to other like radio sequence, etc. So and this is along the same line, talking about quantitative imaging. So with deep learning, we were able to actually get a T1 map, T2 map, basically using one single like conventional T1, T2 image. Okay, so in terms of application, imaging, segmentation, and also planning, essentially the whole radiation therapy workflow actually going to be changed by deep learning. Segmentation, a lot of people work on that. I'm not going to talk about it, but I just want to mention that we're not really solving the problem completely yet. You can tell with all the commercial product, the dice coefficient is still around 80, 90. So we still have some way to go. I think we need some new breakthrough really to move that forward. Planning, I'm gonna skip that. But image guidance, this is actually where we are today, right? When you do like a SBRT, you have to implant a fiducial, but with deep learning, you can actually see what you don't see by the eye, okay? So prostate, pancreatic cancer, you don't have to have a fiducial in order to see the tumor in the projection image. So just last topic, I just want to mention that we're also working on using deep learning to predict immunotherapy response. This is the net, or pretty much the input. It's the gene mutation information, and also the gene interaction map, so that and plus image, you can actually predict who's going to be respond to immunotherapy, who will not. I think my time is up, but yeah, we are also actually trying to bridge the gap between the image and the data. And this is actually a work that we're working on that along the line. So I think I'm gonna stop here. Okay. The last one is really, I want to draw your attention. It's actually along the line of a barbarism that Matt nicely put together. Really, I think we are moving toward data-centric deep learning, and also deployment to the clinic. It becomes essential. And with that, I think I'd like to acknowledge my colleague and thank you very much.
Thank you, Dr. Shi. Appreciate it.